All right, recording is rolling. Welcome to Friday, October 6th. There are a couple of rocket launches scheduled today. One at 2 p.m. during the school day. I think that'll be, yeah, during the pep rally. We've got pep rally 7th period, right? And then one Friday night, late at night, about 10:30-ish. Right, so yesterday, you guys were swinging these canisters around in circles, and see there was some mass going at some speed in a circle of some radial size, and there was some weight down here that was holding everything in balance, right? This hanging weight was in true static equilibrium, it wasn't moving. The swinging mass was not in true static equilibrium because it was on a curved path. You might sometimes hear the phrase like dynamic equilibrium because this radial size wasn't changing, right? But I split you guys up into 3 experimental groups to say, well, what's the relationship among these 4 variables, right? So we're going to put these graphs together today, these graphs, right? We're going to do 7 graphs we're going to do. Okay. Have you guys turn these into the grade tray in a class, and yeah, we're going to see if we can come to some conclusion here, okay? Right, so however much paper you want to use for these graphs, all right. I'm going to blow these up bigger for the video. So these 3 with the spades, I'll do right here. Right, so if you got the spades, if you were changing out what was the spade? Was it the swinging mass, I think? All right, I'm about to get some data from you. Set 3 graphs side by side for the spades. We're about to do the spades. Right. So the first one on the spades is, right, what was the speed as a function of the swinging mass? All right, so how about Caitlin, you got some data? Right. What was your fastest speed? What was your fastest speed?
300.
All right, speed in centimeters per second, you said 350 something. All right, I'll go, ooh, this will work. Bam, 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 bam. Right. So 0, 2, let's go 100, 200, 300, 400. I should contain the data there. Okay. And then what was your largest mass? 82 grams. All right, that's a little bit slower. All right, let's go 20, 40, 60, 80, 0, 20, 40, 60, 80. Right. Mass in grams. All right. All right, so let's plot some points. All right, what's one data point?
42 grams and 357.
You said 42 grams? 32 grams? And then, sorry, what's the speed? 357. Okay, so 32, 357, bang, it's right about there. What's another data point?
42 and 347.
42, and sorry, what was the speed?
340.
343? 343. Oh, okay, so maybe right about there. What else you got?
62 grams and then 302.6 centimeters.
Yeah, 2.6, bang, right about there. Okay.
And then 82 and then 275.6 centimeters.
75, bang. All right. Just so far. Okay. All right. Yeah, guys, does that look like probably some kind of inverse relationship? Okay. So as that swinging mass, let's find the visual here. As that swinging mass gets heavier, 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 you got to like swing it slower, slower, slower. I think that makes sense, right? That's for some set radius and some hanging weight. This guy gets heavier, you have to swing it slower, right? Or the opposite, this one gets lighter, you have to swing it faster, right? So I'm suspecting some kind of V is proportional to 1 over MC, some version of that. So that's going to lead to this next graph. We're going to graph what is the speed versus the reciprocal of the mass. Now the speed axis will be the same, so I can just copy paste that speed in centimeters per second. This can go 0, 100, 200, 300, 400, 0, 100, 200, 300, 400. Okay, but the masses we're going to do reciprocal. What's your largest reciprocal mass?
1 over 42.
Okay. Let's see what that comes out to. It's like 0.03 something. right? So 0.01, 0.02, 0.03, and then maybe like 0.04. So 1 over the mass and 1 over grams. 0.01, 0.02, 0.03, 0.04. There. All right, let's get some data points. What's one data point here? And 357, right about there. Okay.
1 over 42.
You said 343? 343. It's right about there. Okay.
1 over 62 and 302.
3, 2, 6, probably right about there.
And then 1 over 82 and 27.
And 275, 6, right about there. Ooh, all right. That is also what that graph should look like. So you guys got that? Copy that too? Right. Let's go back to like very beginning of the year. I told you guys like these graphical relationships you'll see over and over in labs today. Okay. Which one do you think that fits? Which one is that? This guy right here, right? Right. Because we got a bunch of points that, like if you assumed a linear relationship, it might have a huge y-intercept. But then you thought logically, I mean, like, well, it wouldn't make sense for like some speed to approach for one of the mass to go to 0. So that'd be like infinite mass, there'd be like some set speed. So it's not quite linear. It's probably, yeah, it's probably doing some version of a square root type, right? Something like that. Let's say you suspected a square root. So I'm suspecting v is proportional to maybe the square root of 1 over n, right? Now, remember, there's 3 different experiments going on. Kind of how this is all leading is everything's going to be proportional to the speed squared at some point. Okay? There's different ways to do it, but that's kind of the most straightforward way. So I'm going to go speed squared. Now, guys, if I square both sides, okay, then this just turns into 1 over n. Wouldn't that be? Right. So I'm suspecting that's going to be true. Let's do that for the last graph right here. I'll do v squared versus the reciprocal of the mass. All right, so now we're going to be like 2 iterations away from the original data. So this 1 over m and 1 over grams, that can be the same axis as before. I'm kind of running out of paper. I'll have to shorten it a little bit, but I guess it should kind of fit in there. So 0, 0.01, 0.02, 0.03, 0.04. Okay. Now these values squared, if you did meters per second, you'd get more manageable, like smaller type numbers. These will just be large numbers, but that's okay. 400 squared is like 160,000. Okay, so I'll just make the speed squared and centimeters per second being squared go up to like that big, 160,000. Right? So, okay, so go 0, 40,000, 80,000, 120,000, 160,000. Okay, so that should contain all the data right in there. Okay. So you have some data points for this one. Right. What's one data point?
1 over 42 is 167.
130. Can you do that last number again?
127, 400.
127. Okay. So it's probably pretty close to right there. All right. Close to that.
1 over 42 is 117,800.
117 something. It's right about there-ish. Okay.
1 over 62 is 91,500.
You said 90 what?
1,547.
91,000 something. 61,000. It's right about there. Okay.
And then 1 over 82 is 75,947.
79,000. So 75,000? 75,000. All right. All right. That looks pretty good. Pretty good. Okay. Does this one should line up like a straight line? Ooh, that is pretty dang close. It's pretty dang close to a straight line. Okay. So, you got 4 data points, but they're pretty close to telling the story that the textbook would tell, which is that this should be true right here. V squared should be proportional to the reciprocal of the swinging mass. Right? That is pretty good right there. Right? Let's check out my last class, because you guys my second period class. My first period class, they got like pretty much the same story on that graph right there. Okay. Hang on a minute. All right, so got that right. All right, let's do next graph.